Okay, so this rough diagram over here represents Niels Bohr's idea of what an element looks like. So the n equals 1 right here, this would be considered the ground state. This is the lowest possible energy level that an electron can be at. It can't be any closer. It can get further and further away, but it can't get any closer. So ionization potential, what that is, it's the energy in order to liberate an electron from the atom. So there's some electron, let's say it's right here. There's some electron and it's in the n equals 2 orbital. This electron is trying to get away. So this electron tries to escape, but it needs a certain amount of energy. How much energy does this electron need in order to escape? That's the ionization potential. And if you open up your reference tables, or your reference chart, and you go over to the modern section, we're going to see some diagrams right up here. So to the left is our hydrogen, and it has the entire energy level, and as well, mercury, we have the entire energy level. And here I have it right here. So take a look at this. Oh, sorry for that. Okay, so take a look at this, and we have a bunch of different states. So right here is our ground state for hydrogen, and right here, this is the number. This represents the amount of energy in electron volts it takes to ionize an electron at n equals 1. So there's some electron, and it's at this state. It needs 13.6 electron volts in order to release it, in order to free it. So the way I like to think of it is it owes 13.6 electron volts of energy. It can't get away until it pays off its debt. It can't get away until it pays off 13.6 electron volts. If something was at, let's say, the n is equal to 3 energy state, it would only owe 1.51 electron volts. So it would need a smaller debt to pay off, to be released. Pretty cool. All right. So we just started going over this. What is the energy needed to release or ionize a hydrogen atom that's located in the ground state? Well, even though it's negative, that's the debt. It needs 13.6 electron volts. What about if the hydrogen atom was in the n equals 5? Well, we look at n equals 5, we make sure it's hydrogen, and we scroll over. And even though this is negative, this is the debt, so it needs 5.4 electron volts. Okay, try out this one. Try out this one. What's the energy required to liberate a mercury atom? Okay, so you should have gotten 10.38 electron volts. Well, my next question is, what's the frequency of that? Remember, we learned last time that our frequency directly relates to the energy of the photon. So if we have the energy of the photon, we can get the frequency. Go ahead, try it out. All right, don't forget. Remember to convert into joules. Okay, so we've converted into joules. We now have our final answer. But I want to know, so you should have gotten 2.5 times 10 to the 15th hertz. Great job. I want to know what part of the EM spectrum does this frequency come from. Okay, so we're going to open up our reference table. We're going to go through. We're going to look at this. Okay, well, times 10 to the 15th. All right, go through, blah, blah, blah. And we get ultraviolet. Okay, by now we should know how to do that, so I'm not going to spend too much time on it. Okay, But what happens if we're not ionizing? What happens if we're jumping from one energy level to another? Say we're going from, in this case, we're going from 4 to 2. Well, when we go from a higher energy level, so say 4, over to 2, we're releasing energy. So from 4 to 2, we're releasing energy, or it's emitting energy. And it emits energy in the form of light, whether it's visible or off of our visible spectrum of what we can see. And when we go from, let's say, n equals 1 to n equals 2, we're going to absorb energy. We need to get to that excited state, so we're going to gain energy to get excited. And the equation to figure out how much energy is required as we move from 1, the initial energy state, to our final energy state is this equation right here. And that, if we look into our modern physics section, we already have it. That's our second equation that they gave us. So boom. We don't have to worry about that the initial is before the final, because they give it to us. All right, try this one out. Okay, try it out. Come back to me. Okay? So we write down our equation. We substitute with correct units. And we get a final answer. We got 13.22 electron volts. And it's important to note that it's negative. Okay? Because we're exciting the electron. Well, we're taking an excited electron and moving it into the n equals 6. All right. Try this one out. So it's falling from n equals 6 to n equals 2. This time we got an emitted energy. So we're not putting any energy in. It's energy coming out. Okay, so we got our final answer, 3.02 electron volts. Okay, if you haven't been stopping the video and really trying through these, you're doing yourself a disservice. When I ask you to stop the video and actually try through it so you know what you're getting and what you're not getting. All right, go ahead, try out this one. So this one's a little bit tricky. I want you to try to work through it. Okay, here's some hints. Now, how much energy is required to ionize a mercury atom from the ground state? Well, if we look over here, we know it's 10.38 electron volts. And what's the absorbed energy that we're giving in? 20. Okay, what's the difference between those two? That's our leftover energy. Boom. Now we have our leftover energy. And if we want, we can convert this into a speed, since we know that kinetic energy is equal to 1/2 the mass times its velocity squared. Okay. So we excite a hydrogen atom, and we excite it with enough energy to get a whole bunch of little atoms up to the n equals 4 state. How many possible energy transitions are there? Well, we could go from, we're at 4, we can go from 4 to 3, from 4 to 2, from 4 to 1. We could go to 3 to 2, 3 to 1. We could go to 2 to 1. So there's actual 6 energy transitions possible just within hydrogen. And hydrogen is the most simple atom to look at. So imagine how many different energy transitions there are in all of those more complicated atoms. What do we recall about hydrogen? What's made up of hydrogen? What do we see every day around us? What's giving us light that's made up of hydrogen? Ding ding. It's our sun. And our sun is producing a continuous spectrum. Well, what if we took that continuous spectrum and we were able to break it down? Now we have 6 different transitions. What if we could break those down into 6 distinct energy levels? Well, we can. It's called a bright line spectrum. And this is it for hydrogen. So we have a really low, we have a bunch of others as they're in combination. And here we have sodium, helium, neon, and mercury. And in class, ask me, that's how I know you're going to watch the video. Ask me, and I'll show you a specific spectrum, and we're going to actually go through it together. So if we had a bunch of different elements combined together, we'd see a bunch of these different lines combined together. So the practice regions that you took, or you will take, has a bunch of these together. And I will ask you, what elements is it made out of? Well, by knowing what each individual element is composed of, we can say, oh, well, if we have a line here and 2 lines here, and all of these lines, it must be composed of hydrogen and sodium. That's it for today. Have a great day, everyone.